But the reason that we need them from Gatorade is if we exercise very, very hard and we sweat a lot. Normally when you exercise, you do not need electrolytes, okay? Normally when you exercise, you can just drink water and you will get enough electrolytes from the foods that you eat. But if you are working out in very hot weather, if you are, doing half marathon, whatever, if you're doing something very intense, that might be a situation where you're sweating enough that you want to replenish the electrolytes in your body, and that's when a sports drink could be useful, okay? So I know that when my son went, when he was in elementary school, we had like the track and field event, right? And it's in the hot sun, and there were kids who were like, their leg cramped up, and we needed to have them eat a banana or drink some Gatorade. Okay, that's because their electrolytes they'd sweated too much, okay? You find them in your body, which is why you might need to replenish them. You find them in batteries, okay? You find them in plants, you find them in seawater, because basically an electrolyte is just any substance that conducts electricity due to the freely moving ions, okay? So current electricity is the movement of charged particles. If you have a wire, what are the charged particles that are moving? The electrons. But if you have a solution that's made up of water, which is a polar molecule, right? Will a polar molecule be attracted to, what would a polar molecule do in this electric field here? Let's just say that the water went up to here, and I had a water molecule. What would it do in the electric field? Yeah. It would all rotate, yeah. So you would have the slightly positive hydrogens facing this way, and the slightly negative, and they would all line up in one direction. Now, is that moving charge? No, because they're being pushed and pulled. They're just like lining up, okay? They're not doing anything, okay? However, if you have ions, right? So we've got cations, and we have anions. And those guys, what do they do in solution? So if we have a positively charged electrode over here and a negatively charged electrode over on the left, the positively charged things will move towards the negative, and the negative things will move towards the positives. So this is basically a piece of metal. And this is a piece of metal. Okay. And this is actually really relevant to chemistry 12, okay, because in chemistry 12 we do electrochemistry. All right, and so this is a battery. Okay, so we have a little battery there. And we hook up the wire to the battery, and then we hook up the wire to the piece of metal. That piece of metal is known as an electrode. And your other piece of metal is also known as an electrode. You probably did learn about this in grade 9. Yeah. Was that you, Aaron? Oh, that was Alvin? Okay, good. Good. Somebody else is teaching it too. Excellent. Very happy to hear that. Okay. So we've got these electrodes, and in the water we have these dissolved ions. The cations are going to move towards the negatively charged electrode, and the anions are going to move towards the positively charged electrode. Does this make sense? Yes. And so what are we doing? We have moving charged particles. We have charged particles moving in a specific direction. And that is known as current. So the electrons move towards the positive terminal of the battery, and they move away from the negative terminal of the battery. Does that make sense? Right? Because they're being repelled by the negative and they're being attracted to the positive. And if you look at the electrons, remember they have a negative charge. And if you have a complete circuit, what do you need to have a complete circuit? You need a pathway, a complete pathway. You need a circle essentially. Yes? You can't have like a gap, right? And if you look at this, the negative charges, oh look, the negative charges move that way. And so then the negative electrons move up and then they move around. And so negative charge is all moving in this diagram. Negative charge is moving which direction? Counterclockwise, okay? So the negative charge moves counterclockwise. That's not always the case. So I'll put in this example. Which direction does the positive charge move? Positive charge moves clockwise. Those are equivalent. If a positive charge is moving to the right, then the negative charge moving to the left, those mean the same thing. Yes? It's not a rule, it's just in this example. In this example, if we flip the battery, it would go the other way, okay? It's the electrons that are making it negative. Yes? So it's the electrons entering, it's the end of the battery is negative. So the negative end of the battery repels electrons, and it's the electrons entering this piece of metal that makes the piece of metal negative. Now, to be honest, that charge doesn't stay there for long, because what happens in reality is that the cations go there and they grab that one of the incoming electrons and they turn into a neutral atom. Okay, so that negative charge there is actually quite temporary. Yeah, so the electrode is, technically it's probably mostly neutral, okay? But there are incoming electrons, and so the cations are like, ooh, look, incoming electrons. And quite frankly, if you talk to a physics teacher, they'd probably say my way of thinking about this is not the best way to think about it, but it works. Works for chemistry, okay? Yeah. And same thing over on the right-hand side. As the electrons leave, they leave this positive charge behind, but guess who's coming over? It's these negative ions, and they'll be able to give up an electron, so it'll jump onto there and provide the stream of electrons, okay? How does a battery work? We'll talk about that later, okay? But for now, yes. Eventually you will run out. Yes, and that is when the battery, it's the same principle as a battery. A battery will be dead. once it runs out. And this will no longer conduct electricity once it runs out of positive and negative ions. Yeah. Now, the whole point of this is not to necessarily understand how this circuit works at this point. It's a nice preview for next year, but it is to understand that an electrolyte is a solution that contains, is it electrons? Ions. It's a solution that contains dissolved ions. So that's what an electrolyte is. So this whole page can be summarized in that an electrolyte is a solution that contains dissolved ions. So what kind of compound will give you ions? An ionic compound. So you would need a soluble ionic compound. There is also another type of compound that will do it, and it is an acid. Acids also do this. So you want an electrolyte, you need to dissolve either an ionic compound or an acid. Yes? In Gatorade, there's probably sodium chloride, right? That's just your normal salt. You might find some potassium, some nitrate, stuff like that. You can actually look on the bottle, it'll probably say what it contains. Yeah. Could you make Gatorade at home? You probably could. If you just took like a little orange juice and sprinkled a little salt in it, you'd probably be good to go. You know? Not too much salt. They don't actually put very much in there. I do remember though, there was this one time we were in Spain, my husband and and we had ice cream. Don't have ice cream when you travel, okay? Because ice cream it's one of those things that can have bacteria in it. I was violently ill for 2 days. My husband went and saw the town of Cordoba. I think it was in Cordoba. And I just sat in the bathroom, lay on the floor, pressed my face against the cold tile, and was miserable for 2 days. 2 days later, we needed to go to our next stop. I was well enough to kind of get up, but not super well. I was still feeling like, ugh. And my husband went and got me like a drink from a vending machine, and it just so happened that it contained some electrolytes, and it tasted the best of anything I had ever tasted in my life. My body was obviously like, okay, you have lost every ounce of anything that was in you. you need some salts back in your body. Yeah, so it's a good thing to have actually after you've been, violently ill. It can help replenish your electrolytes. Okay. So electrolytes can be dissolved salts, and salts are ionic compounds. And don't forget, hopefully this is all something that you know already. Ionic compounds are made of either a metal and an anion or ammonium and an anion. That's all good, yes? How do you know if something is an acid? H, or it ends in COOH, okay? So an electrolyte will always start with either a metal or NH4 or H, or it will end in COOH. So here's our ionic crystal. Can this solid conduct electricity? In order to conduct electricity, what do you need? You need ions to conduct electricity. You need ions that can do what? Yeah, they have to dissociate and be separate so that they can move. Can ions in a solid ionic compound move? So I wonder if I have it here. I used to have a lovely little chunk of a crystal, but it doesn't, you know what, I'll find it for you for next day, unless that's it. Oh, look at that. Woo! One year we had a crystal growing competition, and someone drew this, grew this beautiful copper sulfate crystal. Copper 2 is blue, copper 2 sulfate. And we can prove that it doesn't conduct electricity by going and grabbing our conductivity apparatus. Super fancy, right? And it's actually funny because we actually have to go and scrounge incandescent bulbs. It's hard to find them these days, so we're stockpiling them so that we don't like lose the loss of it, lose the use of this. And the thing is that incandescent bulbs, depending upon the amount of current that goes through them, they will glow brighter or dimmer. Whereas with a compact fluorescent or an LED, it's just on or it is off. So these are nice because you can see the degree of conductivity by the amount of light that goes through. So let's start by, actually, should we see if water conducts electricity? What do you think? Think about that, talk with your partner. We're just gonna have pure water here. Vancouver tap water. Vancouver tap water is very soft water. Have you heard of the term soft water and hard water? Hard water. It's not just ice, okay? Not ice. It's water that contains a lot of dissolved minerals. So I remember I used to go and visit my grandparents in Salmon Arm, and the water there tasted disgusting. I could not take it. And when you went to shampoo your hair, you could not get, it would not suds up for you, like it wouldn't foam, right? It would just be like, it would just, and then you had to rinse it out and you're like, okay, there was no foam. I hope my hair's clean. I don't know, you know. And that's what happens if you have some ions in the water, especially like calcium and magnesium. They will actually bind with some of the soap molecules and they will prevent it from sudsing. And they make it taste funny, especially if you're a little kid, right? Little kids, you don't want things to taste different. And when the water tastes different, you're like, what is this? This is horrendous, right? So anyway, what do we think? Yes, no? Whoa, exciting, yes? Yes. And in fact, you know what I'll do? I'll turn out the lights a bit so you can see more clearly. Let's watch the light bulbs. Ooh. Ah. Yes. Stunning, right? Now, I'm going to unplug this for a minute because I want to dry off the electrodes. And if I leave it plugged in and I dry off the electrodes, do you remember where I said we found electrolytes? In a human body. So doing this would not be the smartest thing to do unless it's unplugged. It's just unplugged. Okay? So, okay. Now, where's my little crystal? Here it is. Here's our little crystal. Now, you guys predicted that this would not conduct electricity, yes? Why not? Can this crystal conduct electricity? It's made of copper, Cu2 plus, and SO4 2 minus. It has ions, but can they move? They can't move because they're stuck in place. Let's see what happens if I touch these two ends. Oh, look. Nothing. Okay? So much. Well, let's test it and see if it works. Yes? Because maybe it just doesn't work. Now, what if I took some copper sulfate? Yes? Oh, I didn't plug it in. Okay. Yes, let's plug it in. Let's plug it in and see if the crystal conducts electricity. Where did I put the crystal? I keep putting it down. Right here? Okay, okay. Here we go. Let's see. Here we go. Wow, right? I know you can't see past me, but it's okay because nothing's happening. Okay. Now, for the next one, I can actually stand in behind so you'll be able to see. And this one might be a little more exciting. This is copper sulfate. This is copper sulfate, but this is dissolved in water. Okay? And hopefully it's turned on. Woo! Yes? It actually looks like something. Something has happened. Yes? So, we have now separated the ions so they are free to move so it can conduct electricity. And let's just prove to ourselves once again that the water does not conduct electricity. Okay, this is our water here. Nope. Okay. Now, let's try a few other things. I should put this back before I forget. There we go. What have we got here? KSCM. KFCN. What do you think? KSCN. K and then SCN. Potassium. Scandinavium, sure. thiocyanate. It's SCN minus. I know for a fact you've had to draw a Lewis structure of that, but other than that, you may not have come across it. Okay? I've now rinsed this out with just regular water. I'll do it again just to make sure. Okay? There's a big beaker in there right now. Okay? You're going to predict, tell your partner what you think is going to happen with this potassium thiocyanate. Oh! Now, that was 1 molar, 1 mole per liter. 1 molar, 1 mole per liter. Okay? How many moles per liter was our copper sulfate? It was 0.1 molar. Okay, so the copper sulfate was 0.1 molar. Let's try some ethanol. Ethanol. Quick little review of organic chemistry here. F. Hey, hey. F. 2 C's. And then we have the OH, the alcohol. And then what else do we have? 5 H's. Okay, so we have C, C2, H5, OH. You're going to predict to your partner whether you think that is going to conduct electricity or not. Oh yeah, the whole time here. No, I'm just picking them out. Will it, won't it? Okay, are we ready? Wow, that was disappointing. How do you recognize the formula of something that will be an electrolyte in solution? Acid or ionic? Is that acid or ionic? You. Okay. Yeah, we're going to do another one. Oh my gosh, of course, yes. All right. I'm just rinsing it off with water in between times. Okay. Okay. Oh, I have a base here. KOH. Chat with your brother, decide what you think. Drum roll, please. Drum roll, please. Nice and bright, yes. It's a base, but a base is just an ionic compound where the anion happens to be OH. All right. Let's put this one back. Where is it? There's the KOH. One molar ethanoic acid. What is ethanoic acid? We got how many carbons? 2. And what goes on the end if it's an oic acid? 2, 2. COOH. So we have CH3COOH. Anyone know the common name for this? Vinegar. That's vinegar, also known as acetic acid. Okay? So let's give this a try. This is 1 molar acetic acid. Where did I put my little... Oh, here, I'll grab another beaker. That'll be fine. Is it going to or is it not going to? Whoa, that's something new and different. It's the same concentration as the base that was 1 molar NaOH or KOH. It's the same concentration as the KSCN. But what do you notice about the light? It's dimmer. We'll talk about why very shortly, okay? Should we try a more dilute form of CH3COOH? Okay, let's see what that does. Probably, but we want to see it, right? Just to see what it looks like. Ten times diluted. 10 times diluted, so it's 0.1 molar. 10 times diluted. 0.1 molar. It's still acetic acid. Okay? So you expect this to do what? Light up, be dimmer. Let's see if it does. It's, let's see if this even smells like vinegar. Oh yeah, kind of. I'm gonna get a stir stick and see if I can get it going. No, it's not gonna go. No. Yes. Huh? Yes. half and half here? Because we got lots. So let's do it. So this is approximately a 0.5 molar. Not exactly, but approximately. Let's see if we get anything happening here. Okay, but it's really, really dim now, yeah? Next one. Okay, what do you think? Think about this one, 0.1 molar HCl. No, not in a wire. Because remember the wire, you have the cations with the sea of mobile electrons. No. Okay. Sorry, I poured the wrong one. That's why it's taking another minute. I'm like, that's the acetic acid. I don't want that one. We are doing 0.1 molar HCl. I would really like you to predict what's going to happen with that. We just did 0.5 molar acetic acid. Now we are doing 0.1 molar hydrochloric acid. So make a prediction, tell your partner what you think is going to happen. We just did 0.5 molar acetic acid. This is 0.1 molar hydrochloric acid. Are we ready? 5, 4, 3, 2. So obviously the story with the acids is more complex than the story with the ionic compounds. We had one ionic compound that was 0.1 molar, it was very bright. We had an ionic compound that was 1 molar, it was very bright. We had the base that was 0.1 molar and it was very bright, 0.1 molar, very bright. But the acids, we had one acid, even when we had 1 molar acetic acid, was it super bright? No, it was kind of dim, right? And then when we had hydrochloric acid at 10 times diluted compared with that, it was very bright again. So something different happens with acids that we're going to talk about. See if you can think about what that might be while I get this cleaned up, okay? Oh, actually, before we do, we are going to try some sugar water. Okay, so this is sugar. C12H22O11. C12H22O11. Dissolved in water. Okay, so we have this solid ionic crystal lattice. The ions cannot move, so solid ionic compounds cannot conduct electricity. But when we dissolve them into water, do you remember we looked at this near the beginning of the year? The ions actually dissociate. Do you remember that word? Okay, they dissociate. Oh, that's not the one I wanted. I want a highlighter. And they dissociate into free floating ions. And in the absence of an electrical field, these ions just move about randomly. Okay, they just like go whichever direction they want to go. But if you put them in an electric field, then what you end up with is what we saw on that first page, where the cations go one direction and the anions go the opposite direction. Okay, so that's an aqueous ionic compound. And we write the dissociation equation. I know it's right there, but I'm going to write it anyway. So when NaCl dissolves into water, what do we get as the product? Na plus Cl. And what have we forgotten? The plus and the minus. And what else have we forgotten? Aqueous. So this is the dissociation equation. Okie dokie. All right. Acids. Aqueous acids, as we saw, both the acetic acid and the hydrochloric acid did conduct electricity because they also dissociate into free-floating ions. So here is some HCl gas. And what happens when we put it into water? It dissociates. So we started with HCl gas. We dissolve in water. And what do we get? H plus, yes, plus Cl minus, and what have we forgotten? Aqueous and aqueous. Okay, excellent. Covalent compounds are not electrolytes because they do not dissociate in water. Okay, we could watch this video, but I think we watched it earlier this year. Okay, so I don't think we'll spend the time again. Sodium chloride does dissociate, but the sugar molecules stay intact. So if we were to write the sugar, C12, H22, O11, and we were to dissolve it in water, what would the products be? H22O11 aqueous. We've just broken the intermolecular forces between the solid sugar molecules. Yes? Okay. Now, here is a covalently bonded substance that actually is partially soluble in water. It's iodine solid, right? So we have intermolecular forces. Those intermolecular forces break. And then we have dissolved I2. So this would be I2 aqueous. If you need a word to describe what happens to covalent substances, you can say they disperse rather than they dissociate. Dispersing just means like spreading out, okay? Sugar and iodine are neutral molecules, so therefore they will not conduct electricity. Covalent molecules are non-electrolytes. Water is a non-electrolyte. Why? Why is water a non-electrolyte? It's covalent. It doesn't have, there's no separate positive and negative charges. Polar molecules align in a field. That's very nice. You can watch these videos if you want to. Dissolving of sugar, dissolving of salt, movement of sodium and chloride. Can I assign these exercises? Okay, very good. I'll put it on Teams as well. Yep.